Let's talk about quantum tunneling. Quantum tunneling is a phenomenon we observe in quantum physics, where particles are able to move through boundaries or barriers they wouldn't be able to classically due to their wacky quantum properties. It's the reason our sun shines. Without quantum tunneling, the fusion reactions between the hydrogen nuclei, or protons in the centre of our sun, would not occur due to the electromagnetic repulsion of the light charges. However, fortunately for us, the wave-like characteristic of a proton makes it possible for two to exist close enough together that the strong nuclear force can overcome the repulsion and fusion can occur. But wait a minute, aren't we taught that quantum particles like protons and electrons are solid spheres? How is it possible for them to act like waves? The issue arises when trying to make particles analogous with objects we observe macroscopically in classical mechanics, which exist in a given position. Imagine a football being thrown at a door. In this case, the football represents a proton hitting a barrier of some potential energy. Unless the ball is given enough energy to plough through the door, it will simply bounce off it. However, in reality, what we think of as solid particles, or the football in this case, are actually probabilistic regions of space in which the particle doesn't have a well-defined position. This means that the particle can exist anywhere within this region, including, importantly, on the other side or inside of the door. This probability distribution, known as the wave function, is described by the Schrödinger equation, which was derived by Erwin Schrödinger in 1928. When an observation is made in the aforementioned region of space, this so-called wave function collapses and the position of the particle becomes defined for that instant. The square of the amplitude of the wave function at the point of observation determines the probability of it being observed, meaning it becomes increasingly likely for particles to exist at points where the amplitude is larger. So how exactly does quantum tunneling work mechanistically? As a particle nears a barrier of given potential, the wave function passes through the barrier, which causes the amplitude to decay. This makes it less likely for the particle to be found within or past the barrier, but since the amplitude doesn't decay to zero, there is still a probability it can exist in this region. It is important to note that while the amplitude decays, the wavelength doesn't, and therefore the energy of the particle is conserved, meaning the properties of the particle remain unchanged. While this effect as a whole may seem like a weird and esoteric part of quantum mechanics, it actually has many applications in the real world. Technology and touchscreen phones exploit quantum tunneling to function, as when a user touches the screen, the particles of the polymer inside are compressed. This decrease in distance allows electrons to flow inside the polymer by quantum tunneling, as the probability of tunneling is greatly increased. In general, every angstrom the particles move closer together produces an increase in tunneling of a factor of 10, turning the polymer from an insulator to a conductor. No, not that kind. Or that kind. Yeah, that kind.